But to be thorough, okay. To be thorough, let's just review the very first fundamental theorem of calculus that we learned. So you're integrating over a region which is just an interval on the real number line, and you're integrating a derivative of some function, so that's going to be the antiderivative at the upper bound minus the antiderivative at the lower bound. So we see that our derivative here is 3x squared. The antiderivative is x cubed. So this would just be b cubed minus a cubed. Okay. So then you had the one for the next one, right, was the one for line integrals. So this is where you're doing a work integral over some path in space, and you have a starting point and an ending point. Okay. And for the fundamental theorem of calculus there, what you're doing is you're doing a work integral of the gradient of some scalar field. Okay. Along the curve. And so that turned out to be just the scalar field at the terminal point minus the scalar field at the starting point. So a definite generalization of the first fundamental theorem of calculus. So for example, you could be asked to find this work integral over a path where the path is along this circle. That's wrong. Let's make it z with y equals 0, and starting at 0, 0 minus a, and ending at 0, 0 a. So in other words, you have a circle in the xz plane, and let's say x is positive. Okay, so you have a circle in the xz plane, and you're integrating, doing a work integral starting at the point on the negative z-axis, moving along the path where x is positive and ending on the positive z-axis. Okay. And instead of trying to parameterize this, we can notice that if we think of this as f, the vector field, the three components, right? So we're essentially doing this work integral. If this vector field happens to be conservative, then we know that that f is equal to the gradient of some scalar field, and then we could apply the fundamental theorem of calculus for line integrals. And indeed, I won't do it to save time, but you would compute the curl of f, and you get that that is 0, so that implies that f is conservative. The integral is going to be path independent, only the starting and ending points matter. So we could in fact just choose any path we want, or we could have chosen, if you'd like, you can just integrate, right? If you know the vector field is conservative, then you know that the work integral, this path, oh gosh, different class, is path independent. Okay. So this means that we could choose any path we want from the starting to the ending point. So indeed, I could choose the path that's along the z-axis. Okay. So I could say, okay, x will be 0, y will be 0, and z will be equal to t, where t will go from minus a to a. So that way, dx is just 0, dt, if you will. dy is 0, but dz is equal to dt. So you can take your integral. Okay, I guess that's good enough. Let's just put it here. Okay, you can take your integral, and because you realize the vector field is conservative, its path, the work integral is path independent, and you can choose whatever path you want. So you can choose the simplest one, and I just chose the one along the z-axis. So that would mean that y is 0, dx is 0, doesn't matter. X and y are 0. Z is equal to t. dy is 0. This is 0. And finally, we get something that's non-zero. dz is equal to dt. T goes from minus a to a. Okay. Alternatively, we could have found the potential function for this conservative vector field. So that is to say, we're going to find a real valued function such that its gradient gives us our vector field, which we confirmed is, well, we didn't confirm, but I'm telling you it's conservative. Okay, so this means in particular that the derivative of f with respect to x is y squared. So we recover f by anti-differentiating with respect to y. Sorry, x. Sorry, because it's a derivative with respect to x, so we anti-differentiate with respect to x. And we get xy squared plus, instead of a constant of integration, you get a function of the other two variables, right, y and z. And then we differentiate f with respect to y. So here's f, differentiate that with respect to y. And we know that it has to equal to our second component of the vector field. And if we're doing things correctly here, then any function of x should cancel out, right? Because this means that because h was just a function of x and y. And to recover this h, we know its derivative with respect to y, so we recover it by anti-differentiating with respect to y. And then instead of a constant of integration, we get a function of the third remaining variable z. Okay. Beautiful. So now let's update f. F is xy squared plus, oops, I don't need to do that, h, whoa, h1, which we found. So h1 is y z squared plus some function of z. So finally, we can differentiate f with respect to the z. So that's 0, that's 2yz. And this is derivative of h2 with respect to z. And we know what that should equal to, the third component of our vector field. And any function of x, y should cancel. It should just be what should remain is just some function of z as advertised. h2 is just a function of z. So we recover h2 by anti-differentiating with respect to z. So z cubed, up to a constant. I can make that constant 0. So now we finally found a good potential function. So xy squared plus yz squared plus h2, which we found is z cubed. Okay. So that's a lot of work. But then that work integral of our vector field turned out to be the gradient of the scalar field here by the fundamental theorem of calculus for line integrals. It's just the terminal point minus the starting point. Our potential evaluated at the terminal point minus potential function evaluated at the starting point. So this was 0, 0, a for the terminal point. And this was 0, 0 minus a. Okay, so once again, you just get a cubed minus, so luckily we got the same thing, right? As should be the case. Okay, all right. So that was the second kind of manifestation of fundamental theorem of calculus for line integrals. Okay, so that's that. So now we should do maybe Green's theorem. Okay. For the plane. Okay, so this is where you have a region in the plane, and then you have a bounding curve enclosing that region. So let's call that boundary of R. And this boundary has a counterclockwise orientation. So that's going to be important. Okay. And so that fundamental theorem of calculus says that that integral over that closed curve counterclockwise, and you're doing some work integral, is the same as the integral over the two-dimensional region itself. And what you'd be integrating is the derivative of q with respect to x minus the derivative of p with respect to y times the differential area element. Okay, so that's Green's theorem. And notice that if we have a vector field with on the plane with components p and q, what does it mean for f to be conservative? Well, it means that the derivative of q with respect to x is the same as the derivative of p with respect to y. So that means that on the right-hand side of Green's theorem, this quantity here would be 0, right? so that for any conservative vector field, the work integral around a closed loop is 0. Okay. Right, so let's do an example of Green's theorem then. So let's just keep it really simple. What do you mean by, what do you mean the vector field is bounded? You mean the components of the vector field are bounded functions? No, they don't have to be bounded. I'm not sure what you mean exactly. Let's see. Like, so here's a vector field I'm going to be working with. It's not bounded. It's bounded. Oh, okay. It should be the vector field. You don't want it to have singularities in the on this region. So you don't want the denominator to go to 0, for example. So if you had a vector field like, I mean, just some classic examples, I guess. Right? You couldn't apply Green's theorem if what is true? If your region contained the origin, right? Because then your function blows up. Right? So Green's theorem would not apply. So yeah, I didn't state a lot of the prerequisites, right? But your function has to be continuous on this region. Differentiable. It has to be C1 everywhere on the region and on the boundary of that region. So if that's what you meant, yeah, it's right. You're correct. Okay. So, but I chose pretty simple vector fields. We don't have these problems, but it's definitely good to look out for that. So here's a vector field. And what we're going to be trying to do is find a work integral over some triangle from the origin to the point A0, and then up to the point AB, and then back down to the origin. So notice this has an orientation that's counterclockwise. Okay. And then our region would just be the enclosed is just this triangle. Okay, and so what we might be asked to do is to do the work integral over the, so if this is our triangle, T, then the green boundary is just the boundary of the triangle, right? And we might be asked to do a work integral of the vector field over that boundary. This also might be written as, I hate this notation, but T, right? Okay. Now, we could do this integral for sure. It's not that hard to parametrize the three sides of this triangle and actually do this work integral directly. It's not that hard. But we could also apply Green's theorem, because this is negative y dx plus x dy, right? So your vector field has two components, and this ds, you can think of it as dx dy. And when you take the dot product, you just get the work integral written in the differential form. Okay, so according to Green's theorem, this is the same as the double integral over that triangular region. And we take the derivative of, so remember, P is the thing that multiplies dx, Q is the thing that multiplies dy. So Green's theorem states we differentiate Q with respect to x, if I can find the Green's theorem. Yeah. Differentiate Q with respect to x. So that would be derivative of x with respect to x minus the derivative of P with respect to y. So that would be the derivative of minus y with respect to y, so -1. Okay. And so really we don't have to do anything here because this is just a constant times differential area element. So this should be 2 times this integral over the triangle of the differential area element. Just gives us the area of that triangle. So this should be 2 times, then 1/2 base times height. So a times b. Okay. So that's a times b. And for practice, you can try to do the work integral directly by parametrizing each side of our triangle and integrating. Okay. 2. Okay. Right. Okay. So that was a quick example of Green's theorem. You really want to get to the neat stuff in 3 dimensions, right? So the next manifestation of fundamental theorem of calculus, so I guess there's in your class curl theorem, Stokes theorem for the plane. So what does that say? You have some curve and you give it an orientation, I guess, by giving it normal vector. I'll use your notation. Okay. So so what is that? Oh, 1 second. Curl. The flux of the curl. Oh, wait a minute. Let me just 1 second. So so this is divergence theorem, I guess, for the plane. So the integral over the closed surface of f dot n ds. So the flux of the vector field through here, that would be the same as the integral of the divergence of the vector field over the, so this is the boundary, this is the region. Okay. Some area element. Yeah. So I think you had that in class, but I really wanted to get to Stokes theorem. Yeah. For the plane. Yeah. There's a divergence theorem for 3-dimensional space. That's what we really want to get to. So there's Stokes theorem. So what that does is it takes some surface. So that's our surface S. And that surface has a bounding curve. And now we have to be careful of the orientation here. So I have a unit normal to my surface. Okay. And the idea is that the orientation of the bounding curve, the orientation of it has to match. Oh, 1 second. My machine is acting up. Okay. Gosh dang it. Where did it go? There you go. Okay. So if you use the right-hand rule for that normal, if you curl your fingers in the direction of the curve, then your thumb should be pointing in the normal direction. So in particular, let's say you have some area and you want to do a work integral over the bounding curve that way. If you use your right-hand rule, your fingers would curl that way. So your thumb would be pointing down, so that the normal would have to be pointing down. So the normal for the surface has to match the orientation of the bounding curve. Okay. So what Stokes theorem is going to say is that the work integral over the bounding curve is equivalent to the double integral over the surface of, and it's the flux of the curl of the vector field. So curl of the vector field F and the flux integral. So yeah, okay. So you might have seen this as, I'm not a big fan of this notation. So F dot tangent ds is equivalent to the integral over the surface, and then you have the curl, and then dot the unit normal to the surface area element. Okay. Okay. So let's see if I have an example. Yeah, this is good. Okay. So we're going to look at Stokes theorem. So you have a vector field. And then you have a region in three-dimensional space. It's a region that's the part of the cylinder, solid cylinder. And wait a minute. No, that'll be a surface. So I'll just use S. One is for the first and the second. Difference between the first one and the second one? Oh no. Okay, I see. I know what you're saying. Okay, there is no difference. Is that if you have a curve, we said we have a differential length element, right? ds. It's like a vector, but it's equivalent to the unit tangent times the length element ds. They're equivalent. There's just different notations of the same thing. Likewise, ds, the differential surface element, is both the differential area element on that surface times the unit normal. Right? So this is equivalent to that, and this is equivalent to that. The equations. Okay. So let's see. So now what we want to do is we want to compute the. So let's draw this region, right? You have your cylinder. And then, so it's radius A. And then you have your plane. So in the YZ plane, of course, that's just a line with intercepts A. So what would happen is that in space, the graph is the graph of a plane, and it cuts the cylinder, and it cuts it in some elliptical shape. Okay. So our surface is actually this elliptical disk that's kind of slanted in space. Okay. And the bounding curve is our ellipse here. Right. And suppose that we want to do the integral, so it's the orientation of the bounding curve is this way. So the unit normal, if you use your right-hand rule and curl your fingers in the direction of the orientation of the curve, your thumb would be pointing that way. So your unit normal has to have a positive z component, right, in any case. And it looks like a positive y component as well. Okay. Right. And now what we want to do is actually find the work integral over the boundary of that surface. So that's in green. It's the green boundary. Okay. And we'd be doing the work integral. And so we could parameterize that curve, right? Like x would be a cosine t, y would be a sine t. That takes care of the disk. And z would be, according to the equation of the plane, z would be a minus y. So we could find a parametrization of that green curve, find the derivative, and plug everything in. But that would be a pain. I don't think it's not undoable. But instead, let's see if applying Stokes theorem simplifies what we have to integrate, even though we have to integrate over a two-dimensional region. So here's Stokes theorem. Instead, you're going to integrate the curl of your vector field, and you want to compute its flux through the surface. Okay, so I guess we have to find the curl of our vector field. All right, so differentiate x cubed minus x cubed with respect to y minus the derivative of this with respect to z. That's just 0. Go figure. Okay. So the next component, derivative of x with respect to z, and the derivative minus x cubed with respect to x. So you get 0 minus and minus 3x squared. And the third component, the derivative of this with respect to x minus the derivative of that with respect to y. All right, so we get 3y squared. Okay, so that's our curl. Now, if we want to do the surface integral, of course, we have to parameterize the surface. And there is a natural parameterization, not natural. Think of it as first parameterizing this disk. So let's, well, no. Let's just do this. So here's a parameterization of our orange disk there. This is going to be easier than I made it out to be. So make the parameterization a function of x and y. Where x is anything, y is anything, but z has to be, right? Z has to be a minus y, according to the, because we're in the plane. And of course, our parameter space would be that x and y have to be on that disk of radius a. So now ds, or if you'd like, the unit normal to the surface times the differential area element. We know the formula for that. It's the, we'll have to be careful here because the orientation has to be right. So this is going to be the derivative of r with respect to x crossed with the derivative of r with respect to y, dy dx. Or the other way around. I have to make sure that my normal is pointing upward, right? So let's just compute this cross product. ijk, the derivative of r with respect to x becomes 1, 0, 0. Derivative of r with respect to y, 0, 1, minus 1. Okay. So very quickly, that's 0. Oh, come on. Okay. All right, 0, 1, 1. Yeah, so that works out, right? That has a positive y component, positive z component, so the normal is pointing upward like that. Okay. Okay, so now we have the curl, we have the parametrization, and we found the differential area element, our unit normal, not our unit normal, but our normal times dx, or dy dx. Okay, so now we're ready to do the right-hand side of Stokes theorem. Okay, we computed the curl. Oh, where is it? Okay, we computed the curl, which was right over here. We have our differential area element with normal. And we're integrating over that disk in the xy plane of radius a. So obviously here we'd want to switch coordinates, right? We want to go to polar coordinates. since we're integrating over a disk. And okay, so in polar coordinates, this integrand becomes 3r squared. The differential area element becomes r dr d theta, and to cover the full disk in the xy plane, we know what the bounds for r and a, so r and theta should be. Right, so integrating that with respect to r, 3/4 of r to the fourth at the upper bound, and then with respect to theta, you get 2 pi. Okay. So yeah, so that's an example of using Stokes theorem. Here to do a work integral around a closed boundary, turns out that it was probably simpler to instead do the integral over that disk. Okay. All right, so now the next theorem in 3 dimensions is the divergence theorem. Okay, it's a divergence theorem. Oh, how many did I have already? 1 second. So this Stokes theorem was number 5. Okay. Okay, so now we have divergence. Okay, so this time you have a 3-dimensional blob, so it's a 3-dimensional region. And then you have the boundary of that region, which is a closed surface. So divergence theorem says that if you want to compute the flux of some vector field, through that closed surface, that's equivalent to instead doing a triple integral over the enclosed region, the 3-dimensional region, of the divergence of your vector field. And this is some volume element. Let's just call it dV. So all right, so let's look at, do we want to confirm it or just use it? Okay, so here's an example. So again, we go with a cylinder. So our region is going to be defined by a cylinder. Again, this time z is between A and B. Okay. And so what we want to look at is the surface, which is the boundary of that region. Okay. So we have a solid cylinder Okay. Okay. And the boundary is a closed boundary because it consists of, you have a base, that's a disk. You have, I guess, the side of the cylinder. And then you have the top, right? Let's color it blue. Okay. So we have, to enclose that solid cylinder being the top, the bottom disk, and the side. Okay. And perhaps we were asked to find the flux through that surface. It's important that it's closed, right? There's no, if we didn't have the top, for example, that would not be a closed surface. And we want to do the flux through the surface. Okay. And let's say our vector field is given by okay. So first of all, if you could compute the flux through the surface directly, except you have to break it up to 3 separate integrals, correct? Because you had to integrate over the top, the bottom, and the side. And I should mention this right now because I forgot. The unit normal, so in a surface, you have a normal vector associated, normal to the surface. And to use divergence theorem here, yeah, the normal has to be outward pointing. It has to point away from the surface. So if you were to do this flux integral directly over that surface, on the top, your unit normal would just be positive z direction. On the bottom, that unit normal would be in the negative z direction. And on the side, well, it would be something else, right? That unit normal would be okay. But the idea is that the unit normal in divergence theorem has to be pointing away from the enclosed region. It's an outward pointing normal. Okay. Cool. But instead of doing these 3 separate integrals over the top, the bottom, and the side, and finding parametrizations for each of those, what you should do for practice, right? Instead, maybe we just employ divergence theorem and see if integrating the divergence of our vector field is simpler, even though we have to now integrate over, well, at least it's one whole region, right? Okay. So we compute the divergence, so the derivative of the first component with respect to x, the derivative of the second component with respect to y, plus the derivative of the third component with respect to z. Okay. Of course, the y's cancel, so. And what coordinate system would we use to integrate over the cylinder, right? Well, cylindrical, of course. So we would say, okay, let's use cylindrical. Let's say z equals t or something. Okay. So here z would become t. And what's the differential volume element in cylindrical? That would be r dz dr d theta. And we know the bounds. Full disk. And z is goes from 0 in the xy plane all the way to b. All right, integrating with respect to theta, we get 2 pi. Integrating with respect to t, we get 1/2 b squared. Integrating with respect to z, sorry. And then integrating with respect to r, we get another 1/2, but this time a squared. So that's pi divided by 2 a squared plus b times b squared. So the integration part is trivial. But that was way faster than trying to integrate over three separate surfaces. You should try to see how that works out. Okay. It's doable but laborious. Okay, so that's an example of divergence theorem. Let's do another divergence theorem, but it's one where you apparently shouldn't be using it because you don't have a closed surface. So another example using divergence theorem. Okay. So suppose we have a hemisphere. Call that hemisphere H. And the hemisphere is given by, say, x squared plus y squared plus z squared equals a squared, but let's say where z is positive, so it's the upper hemisphere. And suppose you're given a vector field. So let's do x squared minus 2yx, and then z minus 1. Okay. And what they want you to find is a flux integral through that hemisphere. With upward pointing normal. Okay. In other words, our normal vector, if we have our surface, which is our hemisphere, yeah, that's our hemisphere. I love this Microsoft whiteboard, but it's so darn laggy, man. Okay. So if we have a normal, it'd have to be pointing upward. Okay. Okay. Now, we could try to parametrize the surface, our sphere, and then compute this integral, this flux integral. But it would be better if we could use divergence theorem, right? But why can't we use divergence theorem? Why can't we use the divergence theorem as things stand?
It's not closed.
All right, awesome, thank you. Yeah, we're not including the disk on the bottom, right? So the problem is that there's the boundary of the surface is here. Okay. And we're not including the bottom disk. Okay, so it's not a closed surface. So we can't apply divergence theorem. But what if we did include the bottom, right? Okay. So what if we included the bottom? Let's call that B, or D for disk. That's the disk, right? Then we could apply the divergence theorem. Okay, so instead of doing our flux integral, let's do this one. It's the integral over the hemisphere of the upward pointing normal, plus the integral, the flux integral over the bottom disk. Let's call it D, disk. Okay, now, and what would the normal, so here we have upward pointing normal. What about the normal for the bottom disk? Which direction would it have to point if we wanted to use divergence theorem?
Outward.
outward, so down, right? Because in Divergence Theorem, right, the normal has to be pointing away from the interior, the region. Yeah. So downward normal. Okay, and then we could use divergence because now we have a closed surface, so we can instead integrate over the hemisphere, the half ball. Okay, the half ball, and then would be the divergence of the vector field, dV. Okay, so let's do that first. The divergence over a vector field. So the derivative of the first component with respect to x, then derivative with respect to y, then derivative with respect to z. Well, go figure, right? So the integral of the differential volume element of over the half ball, it gives you the volume of the half ball. And we all know that the volume of a full sphere is 4/3 pi radius squared, so half of that would be 2/3 pi a squared. Okay. So now let's compute. I hope it's not hurting your eyes, man. It's hurting mine. But it's this. I need to get this whiteboard to not be so sensitive to the touch. Okay. Okay. So next, let's do the this integral here over the disk. Okay. All right. So to do that integral, we need to well, we don't need to parameterize, do we? Okay, f, the vector field f restricted to the disk, how can we simplify it? Remember, this disk is in the xy plane. So I didn't draw my coordinates, but I should have, my axes rather. So this disk is in the plane, right? It's a subset of that. So what's true? So z has to be 0. So I can just take my vector field and restrict it to the plane, so I can just let z equal 0. Okay, and without so let's see, how do we find the differential area element with unit normal? Well, we can just guess what it is, right? The unit normal would be downward pointing in the z direction, so 0, 0, minus 1. And the differential area element in the xy plane is just dx dy. So we could just guess, or if you really wanted to, you could parameterize. Right. We could parameterize the disk, which would be very simple. Z is 0. And of course, we're on that disk. And so to find ds, we would compute the derivative of r with respect to x, cross it with the derivative of r with respect to y. And that's a really simple, I know. Oops. Okay. All right. So we would get 0, 0, and 1. So this would be wrong, correct? No, we're not quite right. What's wrong with this? What's wrong with this? Why is this not what we want? Because it's the unit, the normal is pointing in the wrong direction. So I should have had the derivative of r with respect to y cross the derivative of r with respect to x instead, and then that would have worked out. Okay, so you always have to kind of keep that in mind, which way the normal should be pointing. Okay, so then the dot product of these two is just 1 dy dx. So the double integral over that disk, again, just gives you the area of that disk. So that's pi a squared. Okay, so there we go, and we're done. Right? We have the flux through the hemisphere that we originally wanted to compute is unknown. We were too lazy to find that integral, but we found the integral over that disk. It's just pi a squared. That's equal to, according to the divergence theorem, 2/3 pi a squared. So now we can indirectly solve for the flux through the hemisphere. So, yeah. We couldn't use divergence as the problem was stated, but we just simply created a closed surface. And it's turned out that it was easier to do the flux integral through that that face, that surface that we introduced, as opposed to the original surface that we had. Okay, what else did you talk about in class? Does that cover all of them, I think? Line integral, Green's theorem for the plane, and then Stokes, and then divergence theorem for space. Do you have any outstanding questions not involving finding second order Taylor approximations to some potential function? Did you talk about differential forms? Have you started talking about them? Okay. For Tuesday? Okay. So what else can I? Yeah, okay, well, that's all I have then. Unless you have questions, that's really all I have. Anything confusing about my notation that you need clarified? Because there's so much notation going on in these books, right? And okay. Maybe I could, since you're here, maybe I could. That's kind of silly example, but there's an implication of Stokes theorem. Right, so if you have some surface that's weird, that's a surface, and you say wanted to find the flux of the curl of some vector field. As long as that boundary is fixed, you fix the boundary, right? According to Stokes theorem, well, I should say you wanted, yeah. According to Stokes theorem, you can deform that surface. You can deform that surface continuously until you just end up with a disk, say. That's good enough. Purples. Oh. Okay. You just end up with a disk. And then that way that's going to be equivalent, because this integral doesn't change as long as the boundary is fixed, right? So that would be equivalent over a new surface, which is just the disk. And that would be really, so it would be the curl of f, but restricted to S, the disk, dotted with, and here the unit normal would be pointing upward in the positive z direction. So you can simplify the surface over which you're integrating as long as you hold the boundary fixed. Okay. Sure, I can try. What is the integral? You can either type it or say it. I'm ready for the integral. Ah, gotcha. So this is, let's see. Now that's this arctangent function. What's being squared, the x or the arctangent?
It's funny you say that because so this was actually like an exam question from previous, and then this is literally how it was written.
So what's being squared? Do you know?
I have no idea. This is how it's written on the question. I literally copied it exactly how it's written on the question, and the squared is right outside the parentheses.
And so the upper bound, the bounds for the second integral are from 1/2 to 1, and then from 0 to, what does that say?
1 over y minus 1. Wait, hold on. I think the minus 1 is inside the square root.
Okay, gotcha. Now let's look at it if we have time. So, okay. So let's draw the region of integration. So the first integral, and that was dx dy. So the y bounds are from 0 to 1/2, and the x bounds are from 0 to 1. So that's a rectangle. And then the second integral, the bounds are from 1/2 to 1 with respect to y. And then x goes from 0 to square root of 1 over y, I'm assuming, minus 1. That's so weird. That's not even a proper integral, right? Because you have, no, it is. No, it blows up.
Oh, I have a better picture.
So when x is 1, y is a half. When x is 0, y is 1. Okay, so that looks something like, okay. So that's our region of integration. This is on an exam? That's rough, man.
Wait, okay, I shared the correct one right now.
Oh, okay.
This is exactly how it was.
Jesus, okay.
Yeah.
Oh, so that's the whole thing's underneath the square root. Okay.
Yeah, that's what I meant.
Okay, so let's fix that.
Wait, and we can't see what you're doing.
Oh, oh, that's right, because you shared something.
Right.
Okay. Okay, so y would be, okay, so that's the region. Okay. So I guess we could switch the bounds of integration for 1, right? So maybe it didn't matter. Maybe that was the whole point. So let's switch the order of integration. So let's integrate with respect to x first. So x would go from 0 to 1. And y would go from 0 to where y equals 1 over 1 plus x squared. And the integrand was the same in both cases, so it was arctangent of this.
So,
right.
Wait, so are you integrating the right one first? The one
So
after?
I think so I'm pretty sure this is like that. No, I switched the bounds of integration. So the original order, I switched the order of integration, sorry. So originally it was like this.
No, I meant like there's two integrations going on, and they're bringing.
Yeah. I turned it into one. Into one integration. Okay. Because I drew the region of integration and I realized this was x simple. Okay. So instead of integrating with respect to y and then x, I switched the order so it's dy dx now.
Right, but you only did it for the right one, right?
No, I did it for both. So this is integral 1, this is integral 2, this is region 1, this is region 2. I pulled it together into a single region. It's x simple. I pulled it into into a single region. So you just have one integral. So now what you could do is you could integrate with respect to y here, no problem, right? Because there is no y. You just get y times arctangent of x quantity squared, I'm assuming. Because then it works out nicely. And that's from 0 to 1 over 1 plus x squared. Okay. So you just get arctangent of x quantity squared divided by 1 plus x squared. You integrate that result with respect to x, and that's simple because we know the derivative of arctangent is 1 over 1 plus x squared. So you do u sub. So this becomes, so when x is 0, arctangent is 0. When x is 1, arctangent is pi over 4. So u sub. Okay, so whatever that is. So the trick was to draw the region of integration. There were two integrals, but that region of integration can be turned into a single region. That's x simple. if you flip the order of integration. And then after that, it's a matter of a substitution.
See, where I messed up was I did them separate. You know how you combine both of them into one?
Yeah,
I did them separately, and oh my god, it was hell.
yeah. Yeah, I can imagine. I wouldn't know how to.
Because you know how yours is going from 0 to 1 over 1 plus x squared? Mine was going from 1/2 to 1 over,
Oh,
and then you
God.
plug in 1/2. I was like, oh my god.
Oh, yeah.
Yeah, I didn't recognize they would combine like that.
Yeah.
Damn.